So suppose we're tasked now to show that the expected return time to some arbitrary state x is less than infinity. And we're asked to show this directly without relying on any theorems related to irreducibility and positive recurrence, meaning that we can't state, the chain is irreducible, therefore all the states are positive recurrent or none of them are, and then, show that m naught is less than infinity and therefore conclude that mx is less than infinity. Here we're being asked to show this property directly for some x greater than 0. So let's run this calculation. It's it's a good exercise. So what one would do in this case is, we're obviously computing the expectation of a random variable, a trip that a Markov chain, in this case a renewal chain, takes. And so you may want to try to decompose the trip into separate segments to kind of break it down and make it easier for yourself. So let's try to think through what these trip segments look like. So suppose I'm thinking of the state x here. What's the first thing that happens? Before I can return to x, I must first go to 0. Right? That this is what deterministically happens. Right? I count down from x all the way to 0, no matter what. And in bounding this return time, I am going to put an x here, obviously. Right? I'm accounting for the first x units of time that it takes me to go from x down to 0. At this point, I do have a chance to return to x, namely with probability qx. I can also, of course, return by making any move that exceeds x, and that's going to be with probability capital qx. And once, if I do that, then I can definitely make it back to x. But notice that if I, come out to, say, 4, then I have to come back to 0 empty-handed. I would not have returned to x. And this can happen multiple times, right? You can go out to 2, come back to 0, come out to 4, come back to 0, and just keep going and trying again until the very first time that you exceed x. But you know that once the very first time that you exceed x happens, then you're bound to reach x for sure, because then there is a unit probability of counting back downwards. Right, so if any time you come out to any state y that's greater than x, you're going to count downwards, and for sure you'll reach the state x again, returning to your starting point. So now let's talk about what this means in terms of the trip length. Again, the first part accounts for our trip from x to state 0. I'm going to let y be the very first attempt on which we exceed state x. So like I mentioned, we try, right? We come out to various states, and we either fail to exceed x or we succeed in exceeding x. And if we let y be the very first attempt on which we exceed x, that means my trip is bounded by y times x, more accurately maybe even y minus 1 times x. Right? I failed to exceed x y minus 1 times. So if you want an even sharper bound would be y minus 1 times x. And then this final variable here, I'm defining it to be the state that exceeds x on try y. So the very first time I've exceeded state x, I landed on some state, and I'm calling that m. And then my last part of the trip will be m minus x steps to get back, right, to return to my origin. And so, obviously a sharper bound is available. You can have a 1 minus y there that will cancel that x, or you can use this x to cancel this one. The point is that the x is finite, and we're only trying to conclude this statement here. And we can now clearly see that this will be true if the expectation of y and m are both finite. So in the next clip I'll discuss what we're going to try to look at what are the distributions of m and y, and we're going to try to derive conditions under which both of these will true. And we know what we're expecting to get. What we're expecting to find is some condition similar to m naught being less than infinity. And essentially that's true because we already know the answer. mx is finite when m0 is finite. So let's see if we can get that condition from digging into the expectations of these two random variables.